Thanks, David and Pete. Hey, everyone. My name is Ashok Kelliswamy. I work on autopilot and self-driving at Tesla. I joined Tesla back in 2014, so I've been working on this problem for almost 9 years now. Yeah, some of you might be wondering, hey, what does the self-driving got to do with the plan to a sustainable future? But it's actually a critical part of this plan, and here's why. Currently, when the car is not being used, it is sitting idly in parking lots, not doing anything. But when autonomy is truly unlocked, this car, instead of being idle, can go serve other customers. This fundamentally reduces the need to scale manufacturing to extreme levels, because each car is being used way more. But this is no trivial problem. Building a scalable self-driving system is, I think, one of the hardest real-world AI problems out there right now. Nonetheless, we at Tesla have made significant strides in making one of the most general systems at solving this problem. There are 3 main parts to get right to build a scalable problem. First is the architecture of the AI system. Second is the data, and third is the compute. We'll start with the architecture. At Tesla, we are betting on AI, machine learning neural networks to help us build a general vision and planning system. In the early days, we used to have single camera, single frame neural networks that produced some outputs. These were stitched together in some post-processing steps for the planner. But this was very brittle and was not leading to great success. So what we did in the last few years is transition most of our stack into this multi-camera video neural networks. These neural networks take in the live feed from the car in real time of the 8 cameras in the car and produce a single unified 3D output space. There are many tasks that we produce, such as the presence of obstacles, their motion, lanes, roads, traffic lights, what have you. This is one example output that you're seeing here. This is from our occupancy network that predicts the positions of obstacles and their motion. You can see that it precisely captures the swervy, violent motion of this truck next to us. And this helps the planning system to avoid a collision with this object. Some of the tasks, such as lane connectivity, are more complicated to model using naive methods in computer vision. So we don't stop at the computer vision techniques, but we reach out to techniques in other areas, such as language modeling, reinforcement learning, to model this task. This is similar. These networks use similar techniques, such as transformers, attention modules, autoregressive modeling of tokens, similar to what large language models like ChatGPT do out there. With such an end-to-end system of solving perception, we have really removed the brittle post-processing steps and produced high-quality outputs for the planning system. Even the planning system is not stuck in the old ways. It is now starting to use more and more AI systems to solve this problem. The neural network-based planners are needed especially in complicated urban planning when there's a lot of other objects interacting with us. This is, for example, an intersection where we have to turn left while yielding to crossing objects and to the pedestrians crossing the road. We have to do this both safely and smoothly while respecting everyone's right of way and preferences. If this was done naively, each configuration would take 10 milliseconds of compute, and there are easily thousands of configurations to reason about. This would not be feasible using traditional compute. But using AI, we have packaged all of this into a 50 millisecond compute budget so it can run in real time. The second big piece of this puzzle is the data. This is where Tesla has a unique advantage because it can tap into the fleet to access the exact data that can fix the problems. But raw data is not sufficient. In order to train these networks, you need labeled data. You need labels to supervise the networks. And if you only depended on the human labelers, this data would be too tiny to train these large multi-camera video modules. We need lots and lots of data to train these networks. Hence, we have built a sophisticated auto-labeling pipeline that collects data from the fleet, runs computational algorithms in our data center, and then produces the labels to train these networks. Here, you are seeing a 3D reconstruction that is happening by collecting various clips from different cars in the fleet and assembling them, all of them together into a single unified representation of the world around the car. You can see all the lanes, the road boundaries, curb, crosswalks, even the text on the road being accurately reconstructed by these algorithms. We don't have to stop at this kind of reconstruction. Once we have this base reconstruction, we can build various simulations on top of it to produce an infinite variety of data to train for all the corner cases. We have a capable simulator that can synthesize adversarial weather, lighting conditions, and even the motion of other objects to test all the corner cases that might even be rare in the real world. Here's an example of why this data is critical and how we can solve problems using data. So back in the days, for example, in this case, we had some false braking where we thought this car that's actually parked there was going to move into our path, and hence we were precautiously braking. But it is unnecessary because the car is truly parked. So how can we solve this? What we did was we mined the fleet for similar cases where the car had false braking due to some parked car. We added 14,000 videos to our training set. And then once we train the networks again with this new data, it now correctly understands that, OK, there is no driver in this car, hence it must be parked, so then there is no need to brake. And this is a systematic way to solve problems. On the chart on the right side, you can see that every time we add data, the performance improves. And then we can do this for every kind of task that we have in our system. And this is what we call as data engine. We identify challenging cases, such as the one you saw earlier. And there could be other different types of challenging cases too. We mine the fleet for such data, put it through our auto-labeling system, and produce the labels, add it to the training set. And once we have the newly trained models, we deploy them to the fleet. If we rinse and repeat this process, everything gets better and better. The final critical piece is the compute. In order to train these large models in a reasonable amount of time, you need lots of compute. In addition, compute is also required to produce the labels automatically. This is just compute in our data centers. In addition, we also have high computers in the car, which can run up to like 150 teraops of compute. On the back end, we have a 14,000 GPU cluster, and roughly 30% is used for auto-labeling, and the remaining 70% is used for training. We also have a 30 petabyte of video cache, and this is growing to 200 petabytes. All of this is going to significantly increase once we bring Dojo, which is our training computer, on board into this. Just to give a reference, just the occupancy networks that you saw earlier use 1.4 billion frames to train these networks. We have already shipped our FSD beta software to pretty much everyone that has bought it in United States and Canada. This amounts to roughly 400,000 customers who can turn it on anywhere, and then the car would attempt to drive to the destination. It's still supervised, but it can already handle turns, stop at traffic lights, yield with other objects, and generally get to the destination. We have observed that people who use FSD are already 5 to 6x safer than the US national average. Like I mentioned earlier, the solution to scalable FSD is getting the AI architecture, the data, and the compute just right. And we have assembled a world-class team to execute on this. We are pushing the frontier on these three items, and as we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it is used right now.